1. Data explosion. The world is generating data at unprecedented rates due to advancements in cloud computing, the internet, mobile devices, and embedded sensors. 2. Challenges and advantages. Managing this data is increasingly complex, but organizations that can effectively collect, store, process, and analyze it gain significant competitive advantages. 3. Big data. Often seen as a buzzword, big data actually refers to new and challenging data sources requiring advanced analytics to improve products, processes, and services. 4. Growing interest. Big data is seen as a key asset for productivity, innovation, and customer relations across various sectors, including healthcare, public sector, retail, and manufacturing. 5. Defining big data. Big data is characterized by its volume, variety, and velocity, creating technological limitations for existing tools. 6. Paradigm shift. There is a shift in data management practices, necessitating awareness of new technologies and strategies for maximizing business value. 7. Research challenges. Key challenges in big data include ambiguity in definitions and models, lifecycle management, collection to analysis, security, privacy, and monitoring, organizational changes and new skill requirements. 8. Data science. This field involves extracting patterns and insights from data using techniques from machine learning, programming, and databases. 9. Data warehousing. Traditional data warehouses, DW, are fundamental but may need redesigning to handle big data's demands. 10. Big data warehouse. BDWs are characterized by distributed storage, real-time capabilities, scalability, and support for complex analytics. 11. Research gaps. There is a lack of integrated and validated approaches for designing both the logical and physical layers of BDWs. 12. Current trends. The focus is shifting towards technology-driven solutions rather than data modeling approaches, with a need for cohesive, general-purpose methodologies for BDWs. 1. Problem identification. There is a gap between the ideal design of big data warehouses, BDWs, and their actual implementation. Current approaches are often case-driven, focusing on technology rather than structured design. 2. Proposed solution. A prescriptive approach for BDW design and implementation is suggested. This approach integrates models, methods, and prototypes, grounded in evaluated practices. 3. Goals of the book. Present a general-purpose approach for BDW design and implementation. Maintain relevance of data models and methods despite technological advances. Provide an overview of big data technologies and real-world application examples. 4. Research foundation. The approach is developed through design science research. It aims to guide practitioners and inspire further research. 5. Target scenarios. For organizations without a traditional DW looking to implement a BDW. For those wanting to replace an existing DW. For organizations needing a data-driven approach for high interoperability. 6. Objectives. 1. Big data concepts and technologies. Definitions, challenges, and key technologies, e.g., Hadoop, SQL on Hadoop, NoSQL. 2. Models and methods for BDW. Logical components, data flow models, data preparation methods, and technological infrastructure. 3. Demonstration cases. Data modeling examples, batch and streaming data processes, benchmark scenarios, and real-world implementations, e.g., smart cities. Sioux City Project. 7. Specific case study. Focuses on urban systems modeling with big data. Includes data sources and science techniques for improving urban efficiency and sustainability. 1. Increased interest. Interest in big data surged significantly after 2012, as indicated by Google Trends and McKinsey reports. 2. McKinsey report. Big data is seen as crucial for productivity, innovation, and customer relationships across various sectors, including healthcare, public sector, retail, manufacturing, and personal location contexts. 3. Growth of data. Data volume is growing exponentially, with organizations in the US holding substantial amounts of data. 4. Resistance to change. Despite its benefits, some skepticism exists about why big data is relevant now, due to resistance to change and traditional data processing methods. 5. Advantages of big data. Big data offers more transparency, improved business performance, better decision-making, and the ability to refine products and services. 6. Performance evidence. Data-driven organizations often outperform traditional ones in financial and operational goals, as supported by research. 7. Industries impacted. Big data is becoming essential for competitive advantage across various industries, including electronics, finance, and government. 8. Internet of Things, IoT is a significant source of big data, influencing various business environments and applications. 9. Characteristics of big data. Big data presents a new paradigm in data collection, storage, and analysis, but organizations can benefit from data-driven approaches even without advanced big data techniques. 10. Business applications. Big data is applied in various business areas, such as healthcare, personalizing medication, analyzing genetic data, and utilizing unstructured data like medical images. Environment, correlating environmental data with measured values. Public sector, preventing tax fraud, customizing actions, and increasing transparency. Retail, forecasting events, customer segmentation, and logistics optimization. Manufacturing, demand forecasting and proactive maintenance through sensor data. 1. Volume. Big data involves massive amounts of data with unprecedented growth rates. In 2011, data production exceeded historical data accumulation. Storage capacity and new data management methods are required. 2. Definitions. There is no single, widely accepted definition of big data. Definitions vary by aspects such as size, complexity, and the limitations of traditional technologies. Definitions from sources like Gartner, Oracle, and IBM emphasize size, complexity, and processing techniques. 3. Technological constraints. Big data often exceeds the capabilities of conventional database systems, necessitating alternative processing methods. Traditional software and hardware may struggle to manage or process large and complex datasets efficiently. 4. The 3 versus model. Volume refers to the sheer amount of data, often measured in terabytes or petabytes. Data size is relative and varies by type and period. Variety. Big data includes structured, e.g., relational databases, semi-structured, e.g., XML, and unstructured data, e.g., social media posts. Traditional technologies struggle with this diverse data. Velocity describes the speed at which data is generated and the speed required for processing and analysis. Data can be generated in real time or batch modes. 5. Additional characteristics. Value represents the benefits derived from processing and analyzing data. Raw data typically has low value until analyzed effectively. Veracity concerns the accuracy and trustworthiness of data. Inaccurate data can still be valuable if processed with appropriate techniques. Variability deals with inconsistent data flow rates and peaks. Complexity involves challenges in managing data from various sources, including integration and transformation issues. Ambiguity arises from lack of metadata and challenges in interpreting data. Viscosity refers to data flow resistance caused by high volume and velocity. Virality measures the speed of data propagation across networks. 6. Challenges in quantification. Quantifying big data characteristics is challenging. The concept remains abstract, often defined by the limitations of existing tools and technologies. 7. Future outlook. Big data definitions and techniques will evolve with advancements in technology, such as quantum computing. Adapting to new data technologies and strategies is crucial for leveraging big data effectively. 2.3. Big data challenges. 1. General dilemmas. Definition and standardization issues. Lack of consensus on big data definitions, models, and architectures. Commercial speculation versus scientific research. Absence of standard benchmarks. Chichen et al., 2014, Baru et al., 2013. Data utilization. Challenges in leveraging big data across various fields, e.g., scientific research, finance, healthcare. Issues with selecting and valuing data sources, Chandarana and Vijayalakshmi, 2014. Data representation. Debate over whether larger datasets always offer better population representation, Fisher et al., 2012. 2. Challenges in the big data lifecycle. Storage and scalability. Need to innovate storage devices, architectures, and networks to improve data I/O, accessibility, and transmission. C. L. P. Chun and Zhang, 2014. Scalability is essential for handling and analyzing increasing data volumes. Hashem et al., 2015. Data quality and integration. Ensuring data quality and managing data from diverse sources. Integration challenges due to heterogeneity and redundancy. C. L. P. Chun and Zhang, 2014. Jagadish et al., 2014. Data visualization. Need for advanced visualization techniques to handle large data volumes, multiple data types, and interactive exploration. Krishnan, 2013. Russom, 2011. Data mining and analysis. Challenges in searching, mining, and analyzing large and unstructured datasets. Gandomi and Hayter, 2015. Governance. Managing control and authority over vast, heterogeneous data sources. Need for effective governance tools. Hashem et al., 2015.